Hi everyone, my name is Kevin Ko, and I'm an open source community engineer at Prefect, where I work on data workflow orchestration. Today I'm going to be talking about large-scale data validation with Spark and Dask. We'll start by going over what data validation is and when it's used, and then we'll cover two data validation frameworks in Great Expectations and Pandera. Great Expectations is available for both Pandas and Spark, where Pandera is only available on Pandas. For our specific use case, we'll explain why we want to use Pandera on top of Spark. And in order to do so, we'll use Fugue to do it. Fugue is an open source framework that serves as an abstraction layer and lets users write Python or Pandas code and then apply it on top of Spark and Dask. Interestingly, using Fugue and Pandera will show how easy it is to have different validation schemes for each logical partition of data. This is an operation that the current data validation frameworks don't have support for at the moment. So for our talk today, we'll have a case study with this fictitious company called Sloth. And Sloth is a food delivery service. Sloth is interested in using demand price and having demand pricing per location that updates every 10 minutes. But we're also interested in making sure that the prices that are published to our users are not too ridiculous, that they're not too cheap or too expensive. And we'll use data validation in order to make sure that ridiculous values are not pushed out. So first, we'll cover what data validation is. And data validation is just making sure that the data follows some certain assumptions that you may have. As data pipelines get interconnected, data validations are there to catch errors before they happen and ruin downstream processes. So for our specific use case, we'll likely have a model training pipeline where we load data in from the source, perform validation on it to make sure that it meets the requirements needed for model training. And then once we perform the model training, we're sure that everything will go smoothly because the data has already been validated. In this specific case, our model training will be weekly or monthly. The point is that it's not a time-sensitive pipeline, and data validation can be very extensive and take a lot of resources and time because we're not in a rush to push that. We're not in a rush to execute the model training. On the other hand, we'll have an inference pipeline. And this pipeline, as we said, is running every 10 minutes. So we'll load the data from the source, run the model, and get the new prices. And then we'll perform data validation to check if these prices are reasonable before we update them on the app. For our inference pipeline that runs every 10 minutes, we're concerned about the time it takes for data validation to work because we cannot have a process that takes too much time. So for our 10-minute pipeline, we'll need a more lightweight data validation framework. Some common validations that exist. So first, we can check for the existence of null values in columns that are important to have. Second, we can check the schema of our data set. Do we have the columns that are necessary to make predictions? Are they in the correct type? We can check the data frame shape. This is useful for making sure that rows are not dropped during data transformations, that you still have the expected number of rows. And for our specific use case, we're interested in seeing if the price is within a reasonable range. So we'll begin by talking about validation in Spark with Great Expectations. So Great Expectations is available for both Pandas and Spark. For people who are not familiar with Spark, Spark is a distributed computing framework that has data frames that people use when the data size is too big to efficiently handle in Pandas. So a normal workflow would be that people start using Pandas, and as the data size becomes too big, then you would scale to a distributed compute platform like Spark or Dask. Great Expectations luckily has an API for both Pandas and Spark, making it very easy to transition. So here we have a code snippet to demonstrate what using Great Expectations looks like. And this is an example of how you would use it in a notebook. So first you import the Spark DF dataset and you pass the Spark data frame to the Spark DF dataset. The Spark DF dataset inherits from the Spark data frame, meaning that you can perform all Spark operations on it as you normally would. But added to those operations, we also have these expectation methods that come with the Spark DF dataset. And here we're using the expect columns to be between call 1, and we're applying it on call 1, and we're giving a minimum value of 0 and a max value of 95. An interesting thing about the Great Expectations, built-in expectations, is that they come with the mostly parameter most of the time. The mostly parameter tells us what % of records need to succeed in order to make the expectation a success. So in this specific case, we're saying that 95% of records must be between 0 and 95. If more than 5% of the records are not in this range, then that's considered to be a failure. And then there are different result formats that we can get with varying degrees of detail. Here's an example of what the results show. So on the first line, you'll see that the success is false, meaning we failed this specific validation. And then a bit below, you'll see the result. The result contains a lot of information about how many values were missing, what was the missing percentage, how many records did not pass the expectation, what % of that, what % of the total was that. And then it also provides example values of values that did not match, that did not pass the expectation. So in our case, we were expecting a maximum value of 95, and we have 96, 98, 96. A nice thing about Great Expectations is that as you perform your expectations, under the hood, it's creating a an expectation config. And the config is basically a set of expectations that you can then apply to other data sets once you save it, or to the same data set. The expectation config can also be used to generate data documentation, which is a very interesting feature that Great Expectations have. So you can use the data config and create the data documentation to show what validations were run across a data set. And then you can share this with your team in these HTML documents. Great Expectations also has a data profiler, which you can use to explore data that you haven't worked with yet before. And the data profiler will go in and get some summary statistics and get some information about your data that you can then use as a starting point for your expectation in creating a new expectation suite. The UI also shows a lot of the previous validations that were performed and whether or not they were a success or failure. So in general, Great Expectations has a really robust set of features that definitely extend beyond code with this data documentation. And definitely, I would encourage people to check it out because they have a very robust set of tools to perform really extensive data validations. For our specific use case, attaching Great Expectations to model training makes a lot of sense because we can really explore extensively. But for our inference pipeline, we may need something lightweight. And that's why we have to search for a more lightweight framework. And that's where we come in with Pandera. So Pandera is a pandas-only data validation framework. Similar to Great Expectations, it has a lot of built-in validations. And it also has statistical validations. For example, you can see whether 2 columns follow the same distribution. You can run t-tests. A nice thing about Pandera is because it's lightweight and simple, it's very easy to extend with custom validators. Here's an example code snippet of Pandera. So first we have, we import Pandera and we import the data frame schema. In the middle section, we make a new data frame schema and here we specify that the column price should be of type float. And then we run a check that it is in the range of min value 5 and max value 10. So we are checking that price is within the values 5 and 10. Once we define the data frame schema, it's very easy to apply it. All we have to do is call the validate method and pass in the data frame. So here, the data frame that we pass in has a column price and the check will be applied on that column. The interface is very easy to use and extend. Pandera also has decorators so that these data frame schemas can be applied on data frames through decorators, meaning that it won't invade the code at all. So in order to compare the two frameworks that we explored, Great Expectations on one side has Spark support and Pandas support, while Pandera only has Pandas support. Great Expectations has flexible success criteria with most of their expectations. They give very detailed outputs. The data documentation is certainly an interesting feature so that teams can be on the same page on what expectations the data failed in. And then there's also Slack notifications and other notifications that you can get if pipelines failed their data validation. And then you can use the CLI as well to perform your data validations. On the other hand, we have Pandera, which is very lightweight and but easy to extend. For our specific use case with Food Sloth, it makes sense to use Great Expectations in the training side when we need a lot more information with the data documentation. And then for our inference side, maybe we want to use something more lightweight like Pandera, something that will run fast and just easily check whether or not our data passes the standards required. But the problem is that for very large data sets where we're using Spark, Pandera will not run since it only runs on Pandas. So we have to find a way to run Pandera on top of the Spark execution engine. And that's where Fugue comes in. So Fugue is an open source abstraction layer that lets users write code in Python or Pandas and then apply it to Spark and Dask. For those familiar with the Spark user-defined functions, Fugue is a friendlier interface, which I'll be sharing later. Fugue's goal is to allow users to decouple logic and execution. Users only need to write code once in a scale-agnostic way, and then during execution, decide whether or not it will run on Pandas, Spark, or Dask. Now users will be able to just focus on defining their logic and then scaling seamlessly when needed. You can test locally on smaller datasets with Pandas and then have the same code work on Spark in a production environment. Fugue has two interfaces, the Python interface and the SQL interface. The SQL interface will run on top of Spark SQL. Recently released also was a Blazing SQL backend. So Fugue SQL can use SQL on top of the Blazing SQL execution engine also. On the Python side, we can write code in native Python and then have it applied to Pandas, Spark, or Dask. And I'll share a sample code snippet. So here, in practice, if we make a fill NA function, it's probably going to be written in Pandas because Pandas is faster. But here the goal is to demonstrate that our code can be written in pure native Python and then applied on Pandas, Spark, or Dask. So here on the first line, we have a schema hint. And the schema says that we're keeping all the columns, but adding a new column called filled, which is of type double. Schema is enforced in Fugue. So as Fugue performs the Fugue builds a DAG before the operations are performed, and it's lazily evaluated when using the Spark execution engine, similar to Spark. Now, before the operations are performed, there are validations that the DAG does to make sure that the schemas are matching. And then here we define our fill and a function, which takes type iterable iterable of dictionaries, and then outputs an iterable of dictionaries also. Now we can loop through it similar to an iterable, similar to just any standard iterable where we say for row in df, and we create a new, this is creating the new column where we say row filled equals row value, or that value that to fill the NA value, and then we yield this row. Notice that this code is written in pure native Python, and it has no dependencies on Pandas or Spark. There is no framework dependency. Fugue believes that code should not even be dependent on Fugue itself. And then we create the Fugue workflow context manager, and we pass the Spark execution engine. This is where we specify the execution engine that it will run on. We can also use the Dask execution engine, or we can use Pandas by using the native execution engine, which is the default. And then under the Fugue workflow context manager, we just load a file and perform this fill NA operation. Underneath the context manager, there is no dependency on any framework either. Now we can show how to combine Fugue and Pandera. So for the first 3 lines of this code should be very familiar. This was the basic Pandera code snippet where we checked if our price value was between 5 and 10. The middle section of this code is where we create another Fugue transformer where we apply the data validation. As mentioned earlier, the schema is enforced, but data validation operations tend to be read-only. So our schema here is just everything in is the same as everything out. Then for our data validation, all we're doing is getting that data frame schema from earlier and calling the validate method on the data frame that was passed in, and then we return the data frame. Now we can write our Fugue workflow context manager and pass in the Spark execution engine. And then now this makes the Pandera run on top of Spark. So when we do df equals df.transform price validation, we are running the Pandera data validation on top of Spark. And this leads us to the next thing, which is using this setup, it's actually very easy to extend our validation and have custom validations for each logical partition of data. When people are using Spark or Dask, chances are it's because the data is very large. And if it's very large, it means that there is some logical way we can split the data into smaller sizes, which are our partitions. And then we can perform logic specific to each of those partitions. So our motivation here for Food Sloth is that Food Sloth is growing rapidly, and we're, instead of only being in 1 state as before, it's now available in 3 states. And along with that, there's different business logics and different validations that have to be performed for each different location. We want to make sure that the price ranges for each of these locations can be defined independently. And this is something that's hard to do with the data validation frameworks today. With the current data validation frameworks, you have to define a validation on a column level. And we need to do some extra work in order to or perform multiple validations in order to get it to work in this on a partition level. So here we have example data, and there is a clear split between the pricing of the Florida locations versus the California locations. The Florida locations on average are cheaper, and the California locations on average are more expensive. So what we want to do is we want to apply custom ranges for each of the California locations, and another price range for the Florida locations. We want to split this data frame into two based on based on the location, and then apply that validation. So here's an example of how we can easily extend our previous example and perform validation by partition. First, the two price checks should be very familiar again. They are very similar to the Pandera code that we showed earlier. On the first, we have the price check Florida, and it has a min value of 5 and a max value of 10. The second one is the price check of California, where we have a min value of 10 and a max value of 15. And then we can add these price check objects into the price checks dictionary, where the key will be the location, CA and FL, and the value will be the data frame schema. Now we can extend our price validation transformer as before. The schema is read-only, so everything in will be the same as everything out. The first thing we'll do when the data frame comes in is that it will already be partitioned by location, meaning that the Florida data frames will be separated. A data frame with the Florida entries will be separated from the data frame with the California entries, and the function will be applied for each of those separate data frames. So once the data frame comes in and we pull out the location, that location will be the same throughout the whole data frame already. So the first operation we do is we pull the location, and then using that location, we pull the appropriate data frame schema check from our dictionary price checks. And then once we have that data frame schema, all we have to do as before is call the validate method on top of the data frame. Now with the Fugue workflow context manager, we can pass in the Spark execution engine so that we can take advantage of distributed computing and have each partition and run this parallel on the different partitions. And on the last line of code, we changed it a bit by adding a partition. So first, we're partitioning the data frame by location, meaning that the Florida entries will be separate from the California entries. And then we transform it with the price validation. And now we achieved validation by each a custom validation on each logical partition. So to wrap up the talk, we went over data validation, what it is, when you would use it. We talked about two very different data validation frameworks in Great Expectations and Pandera. Great Expectations being a very heavyweight, very robust ecosystem, but in exchange for that, there is some overhead, of course, to using it for everything that it provides. And in cases where we may want a lighter weight validation framework, we can use Pandera for a quick validation. We showed how we can use Fugue in order to use Python or Pandas-based libraries on top of Spark. Fugue can also use Great Expectations to apply partition validation on each partition. We just chose Pandera because to illustrate why you would want to illustrate using a lighter weight framework for data validation. And we showed how using Fugue, you can actually achieve validation on each partition, which is something that none of the existing data validation frameworks offer today. And with that, that's the end of my talk. I hope that you all check out these projects, Great Expectations and Pandera for data validation, and Fugue also as an abstraction layer. And with that, thank you for coming to my talk.